Good evening, fellow scholars. My name is Faith Bratton, and I'll be giving our Module 4, Chapter 11, Transformation, Symmetries, and Tillings. Okay, let's get started. Okay, so for question 1, it said, what kind of rigid formation did, I'm going to call him E because I do not know how to pronounce his name, and Devontae use? Well, as we can see from the representations on your left, the red and the green, we need to know what transition they used to demonstrate their problem, and we need to know what the correction solution would look like. They were supposed to be arranged in the blocks to form a figure with a horizontal line through it. Okay, but they did a misunderstanding. Well, as we can see, if we put, let's say, a dotted line, as we can see in the pink, across the center of a box and spin the whole diagram to the bottom, we would know that they would make a 180-degree rotation, as what he did, as he just turned the block to make it 180 degrees. But to make a reflection, that's not what you use. They moved the blocks in a clockwise motion when they were supposed to reflect it over the horizontal axis. And for our horizontal axis, we are going to use this pink line. But first, what a reflection is as you can see, like how the line is on the left side, then it turns to the right side. So it's kind of like that. They look exactly the same. Okay, so from the question, they were asked to reflect the pattern block diagram shown. A reflection is a mirror image of a diagram. By knowing that we know that the second figure is in the red is wrong, as shown in this picture, a reflection looks like we know the same figure is still the same. See how the figure is on the right? The figure should be on the right also, but on the bottom. That is what a reflection looks like. So that's how they did it wrong and how you should correctly use it. Okay, in this slide, I'm explaining the concept of if you have one line of symmetry, you have a symmetrical shape, but no symmetry. So for this first one, with the figures given, there are 6 figures with a line of symmetry. The rhombus. The rhombus has a symmetrical line when it's placed through the center of it, as you can see with the pink line. When it is folded in half, all the sides and angles match. To know if a figure is symmetrical, it only has one line of symmetry. The rest of the figures all have some sort of line of symmetry, like the hexagon. It is straight down the middle, or it could be a cross. Okay, this triangle, one straight down the middle. So when you fold it together, they're exactly the same. The rectangle has one right down the middle. The half circle has one. And the I think it's the equilateral triangle, I don't remember. Okay, for this slide, I'm explaining that that was the isosceles triangle. And I'm explaining that these are the 4 shapes with rotational symmetry, but no reflectional symmetry. You know that if these figures have rotational symmetry, they can be rotated like 90 degrees or 180 degrees and still be the same figure. So if we rotated this rhombus 180 degrees, it would look exactly the same. So that means it has rotational symmetry. We are now demonstrating the shapes that have one line of symmetry and rotational symmetry. We are first going to show the green shape. Okay, we know that this figure did not have a line of symmetry, but had a rotational symmetry, but not both. So that's not answering the question because it has to have both, but it only has one. The hexagon, which is in black, has more than one line of symmetry, but it's only asking for one line of symmetry, so that's not it either. The rhombus has 2 lines of symmetry and also a rotational symmetry, but it's only asking for one line of symmetry, so that's not it either. The rectangle has more than one line of symmetry and a rotational symmetry. The rectangle has one line of symmetry and a rotational symmetry. The semicircle has one line of symmetry, but no rotational symmetry. And so does the rectangle and then the red figure. For question 3, we need to demonstrate, is Maya correct with her vertex figure? Okay, so this is what she's given us. Well, we know if we have the center of this is 360 degrees, And so we need to figure out if Mai's figure is correct because her figure needs to equal 160 degrees. So we know that the center is 360, but the purple has 8 angles, which is 135 degrees. The green figure is 108 degrees with 5 angles. And then the green is 108 degrees. The blue is 120, and the purple is 135. When you add these together, they come up to 360 degrees. That's not correct. We need 360 because, so that just shows Myra did it wrong. But to fix her problem, because we need to get, because 363 is greater than 360, we need to fix her vertex. How we could fix her vertex is between this green and blue, we need to make a gap, a 3-degree gap, just to take away the 363 minus the 3 degrees, the gap we make, to make it 360 to make Myra's vertex figure correct. On this figure, we have a line from M and a point P, an arc centered at P that intersects the line in the 2 points Q and S, the 2 arcs of equal radii centered at Q and S intersecting at T. Our first question is demonstrate why triangle QPT is equal or greater than triangle SPT. The relationship is true because line PT, as you can see, is congruent to itself, which satisfies that the SSS properly. The next question is demonstrate why SPT is true, because it has a line of symmetry that is also true. They're congruent. That means they're the same. That's why they equal each other. They have the same angles, same figures. And the next question is demonstrate why angle QPT is equal to angle SPT. This figure is true because the relationship is true because the angles are corresponding angles in congruent triangles. That means corresponding angles, they may be different from each other, but they're the same. And the relationship is true because angle QPV and angle SPV and line PV is congruent to itself, which satisfies that SAS property. The next question is demonstrate why angle QVP and angle SVP are adjacent and supplementary. And you want to know why? Because both of them have 90-degree angles, as you can see right here. Here's one line, and here's the other. That just shows the right angle. As you can see where the yellow line is, that is the right angle of both of them. So that's why they are supplementary. They are the same. Okay, for this one, we need to know by holding a ruler, a regular pentagon penta and an equilateral triangle Q or PQR are both inscribed in the same circle centered as O with P a common vertex. The first one, it wants to construct pentagon, the penta, which we did. Then construct the equilateral triangle, which is the red, as you can see, which is PQR. Okay, it wants us to inscribe both of them, which we did, and demonstrate your calculation of how we get the first one, which is 24 degrees. Well, first we need to find the angles of the equilateral and this angle right here. And so we did, it's 144 degrees and 168 degrees. When you subtract them, you get 24 degrees. So that shows that they both have equilateral triangles and they're inscribed at the same circle centered as O with a common vertex. So it equals 24. Okay, Jenny sees that the top and bottom points of vertical cliff face line up with marks separated by 1.5 inches on the ruler. Jenny is about 1/4 of a mile from the cliff. What is the approximate height of the cliff? Okay, so we're going to recall that a mile is 5,280 feet. Notice that there are 2 similar triangles shown in this diagram, as you can see. Jenny sets lines across the ruler to the top and to the bottom of the cliff, making a triangle with the cliff face, which is similar to the small triangle made by the sight lines to the ruler. The distance from her eyes to the ruler over the distance between the ruler markings will be the same as her distance from the cliff to the height. So an equation we're going to use is the one demonstrated. Okay, so we're going to do distance from her eyes to the ruler over distance between ruler markings equals her distance from the cliff over the height of the cliff. Okay, this proportion can be rewritten as the height of the cliff over 1/2 mile, which is 1.5 inches over 2 feet. As you can see, we have demonstrated. Recalling that now we're going to convert both miles and inches to feet in this equation. We know that 1 mile equals 5,280 feet. As you can see, we're going to determine the feet in 1/2 mile. So 1/2 mile equals 2,640 feet. Convert 1.5 feet or 1.5 inches to feet. 1.5 inches equals 0.125 feet. We're going to substitute these values into this equation with the half mile term and the inch term. Okay, and we're going to find the length of the cliff by multiplying 0.125 feet times 2,640 feet divided by 2 feet. So then we'll know that the height is this top corner over here in the left, which is 550 feet. That is all I have for you guys today. I hope you enjoyed my presentation. So thank you very much, and I hope you enjoyed it.